Good afternoon to everybody. We are now in chapter 12 and we will now going to discuss the non-parametric statistics. Tuning in are the group 10 of 12 members. And so without further ado, we will now proceed to the introduction of this lesson.
So what we will learn on this chapter. So at first, of course, we will introduce what is non-parametric statistics, and then the difference between parametric and non-parametric tests, when to compute different non-parametric tests, the appropriate analysis for independent or dependent group designs with nominal data, and then how to compute Spearman's rank order correlation coefficient for ordinal data, how to compute chi-square goodness of fit and chi-square goodness test for independence tests for nominal data, and then the appropriate analysis for independent and dependent group designs with ordinal data. Why are non-parametric tests less powerful than parametric tests? And what are some of the concerns about transforming interval or ratio data to rank data? And then we'll have the summary of the chapter.
Today, I am to present the differences between the two types of statistical tests. Data analysis is a vast ocean, and it is not surprising to know that many people feel confused as to what type of test should be undertaken to analyze their data project, specifically the research. Actually, there are two types of statistical tests. What are those? They are the parametric and non-parametric statistics. To start with, parametric statistics is based on assumptions about the distribution of population from which the sample was taken, whereas non-parametric tests are not based on assumptions, but rather they are used when the assumptions of the parametric statistics are violated, which means that the data can be collected from a sample that does not follow a specific distribution. Let me now share the differences between the two. Try to analyze which is more appropriate to use. The first difference is that parametric statistics assumes that the sample data are normally distributed, while non-parametric does not. For this reason, non-parametric statistics are sometimes referred to as distribution-free. When it is evident that the distribution of data in a study is significantly skewed, non-parametric tests should be used to test the hypothesis. Secondly, parametric statistics has at least 10 participants in each group, while non-parametric can be computed with a smaller number, which makes it difficult to obtain a normal distribution. The next difference is that parametric statistics is used with interval or ratio data, while non-parametric is used with nominal or ordinal data. Interval and ratio data can be transformed to ordinal data, which will be discussed later by one of our members. Another difference, parametric statistics typically assumes that the variances in each group are the same. We learned in Chapter 9 that a more stringent t-test is used when the homogeneity is violated in non-independent two-group, while non-parametric statistics makes no assumptions about the variances across groups and should be used when samples have very different variances. With regards to interactions, parametric statistics can test for interactions between variables, while non-parametric can test for independence between variables and not for interactions. Another difference is that parametric tests are more powerful. They have a greater probability of correctly rejecting a false null hypothesis. However, although non-parametric tests are less powerful, they do provide useful information about the differences between groups or relationships between variables. And for the computations, the last difference, the computations for parametric statistics are much more complicated than those for the non-parametric. Because of the ease of computation, non-parametric statistics are sometimes used as a quick check on a trend before all the data are entered into a file or during data collection, which are easier to calculate. So, those are the differences between the two. I am hoping that I have shared something. The next presenter will discuss the advantages of non-parametric statistics over the parametric.
A blessed day to all. I am Rainiel Espayan and I will continue to discuss on non-parametric statistics. At this time, I shall focus on answering the question, when are we going to use non-parametric statistics? We use non-parametric statistics in 3 instances. Number 1, we use non-parametric statistics when we analyze nominal data, or those that are used for naming or labeling variables without any quantitative value. Secondly, we use non-parametric statistics when we analyze ordinal data, or data that classifies variables that have a natural order or rank. Or thirdly, we use non-parametric statistics when the assumptions of parametric statistics are violated. In other words, when the assumptions of the planned parametric tests could not be met. This table shows the specific non-parametric statistics in analyzing nominal data and the specific conditions when to use this test. For example, we have here one variable with 2 or more categories, or 2 variables with 2 or more categories. All of these tests will be thoroughly discussed later. The next table shows the specific non-parametric statistics in analyzing ordinal data and the specific conditions when to use these tests. For example, we have one variable with 2 independent groups and one variable with 3 or more independent groups. Again, these tests will be extensively discussed later. Non-parametric statistics may be employed as the study's planned analysis, as a complement to parametric tests, or in situations where the assumptions of the parametric tests could not be met. This third table shows the corresponding non-parametric test for each parametric test that could be used when these parametric tests fail. Now the next question we shall answer is, what are the advantages and disadvantages of using non-parametric statistics? Let's look at the disadvantage first before going to the advantages. The main disadvantage of non-parametric statistics is that they are not as powerful as parametric tests. However, non-parametric statistics offer useful information regarding variations between groups or correlations between variables, despite the fact that non-parametric statistics are less powerful. On the other hand, the advantages of non-parametric statistics are the following. Number 1, non-parametric tests are not susceptible to outliers the way that parametric tests are. One outlier can affect a parametric test by inflating the variance and hence the error term. Outliers in correlation can change the direction or the strength of a relationship between variables. But non-parametric tests do not have this limitation because they measure central tendency using ranked data. Number 2, the main advantage of non-parametric statistics is that they do not require restrictive assumptions about the distribution. Non-parametric tests can also be used when you have non-normal, interval, or ratio data, such as data that are highly skewed. Typically, therefore, non-parametric statistics are only used when the data are too skewed to use a parametric test. And thirdly, non-parametric statistics computations are significantly easier and enable quick analysis of data trends.
The appropriate analysis for independent group design with nominal data. An experimental design is a research method that aims to test a hypothesis and ensure that the research is executed in a controlled and scientific manner. This leads to collecting representative data and drawing conclusions. If the researchers follow the appropriate steps and implement the necessary measures, the results may be considered valid and reliable. Remember, an experiment design measures the independent variable's effect on the dependent variable. In an independent group design, think of an experiment and a control group. For the experiment group of individuals, there is a manipulating of the independent variable. To remember these terms, you can think of them as cause and effect values. The independent variable acts as the cause factor in the experiment. It is manipulated variable that is independent of other variables. The dependent variable's value is predicted to depend on the independent variable's changes. It is the effect factor. It is the reliable being measured. Independent group design differs from repeated group design, which uses the same individuals on two or more different occasions for different experiment conditions. In repeated measures designs, all participants do each task. Here are some examples. A theoretical study used an independent group design to test the potential side effects of a prescription drug. The participants were split into two groups, Group A and Group B. Group A was given the drug and Group B was given a placebo drug, one with no active ingredients. From the research, we would expect no side effects in Group B, as no active ingredients mean that the medication will not affect them. In this case, the independent variable is the drug and the dependent variable is the possible side effect of the drugs. The hypothesis: the X causes side effects Y. The independent variable: the drug taken by the individuals. The dependent variable: the potential side effects. Independent and dependent variables in research are generally used in experimental and quasi-experimental research. Here are some examples of research questions and corresponding independent and dependent variables. Research question: do tomatoes grow faster under fluorescent, incandescent, or natural light? Independent variable: type of light the tomato plant is grown under. Dependent variable: the rate of growth of the tomato plant.
Good day everyone, I'm Ariel Madronero from Misamis Oriental and I will be reporting on how to compute Spearman's rank order correlation coefficient for ordinal data. When should you use the Spearman's rank order correlation? The Spearman's rank order correlation is the non-parametric version of the Pearson product movement correlation. Spearman's correlation coefficient measures the strength and direction of association between two ranked variables. Spearman's rank correlation requires ordinal data. Examples of ordinal data are first, second, third, or small, medium, large, or XL. You can also say strongly agree, neutral, disagree, or strongly disagree. Or very often, not often, or not at all. What are the assumptions of the test? You need two variables that are either ordinal, interval, or ratio. Although you would normally hope to use a Pearson product moment correlation on interval or ratio data, the Spearman correlation can be used when the assumptions of the Pearson correlation are markedly violated. However, Spearman's correlation determines the strength and direction of the monotonic relationship between your two variables rather than the strength and direction of the linear relationship between your two variables, which is what Pearson's correlation determines. What is a monotonic relationship? A monotonic relationship is a relationship that has one of the following. Number one, as the value of one variable increases, so does the value of the other variable. Or second, as the value of one variable increases, the other variable value decreases. Examples of monotonic and non-monotonic relationships are presented in the diagram. Why is a monotonic relationship important to Spearman's correlation? Spearman's correlation measures the strength and direction of monotonic association between two variables. Monotonicity is less restrictive than that of a linear relationship. For example, the middle image above shows a relationship that is monotonic but not linear. A monotonic relationship is not strictly an assumption of Spearman's correlation. That is, you can run a Spearman's correlation on a non-monotonic relationship to determine if there is a monotonic component to the association. However, you would normally pick a measure of association, such as Spearman's correlation, that fits the pattern of the observed data. That is, if it shows the relationship between your two variables looks monotonic, you would run a Spearman's correlation because this will then measure the strength and direction of this monotonic relationship. On the other hand, if, for example, the relationship appears linear, you would run a Pearson's correlation because this will measure the strength and direction of any linear relationship. You will not always be able to visually check whether you have a monotonic relationship. So in this case, you might run a Spearman's correlation anyway. How to rank data? In some cases, your data might already be ranked, but often you will find that you need to rank the data yourself. And thankfully, ranking data is not a difficult task, and it is easily achieved by working through your data in a table. Let us consider the following example data regarding the marks achieved in a math and English exam. The procedure for ranking these scores is as follows. First, create a table with 4 columns and label them. You need to rank the scores for math and English separately. The score with the highest value should be labeled 1 and the lowest score should be labeled 10. If your data set has more than 10 cases, then the lowest score will be how many cases you have. Look carefully at the 2 individuals that scored 61 in the English exam. Notice their joint rank of 6.5. This is because when you have 2 identical values in the data, you need to take the average of the ranks that they would have otherwise occupied. We do this because in this example, we have no way of knowing which score should be put in rank 6 and which score should be rank 7. Therefore, you will notice that the ranks of 6 and 7 do not exist for English. These 2 ranks have been averaged and assigned to each of these tied scores. What is the definition of Spearman's rank order correlation? There are 2 methods to calculate Spearman's correlation depending on whether your data does not have tied ranks or your data has tied ranks. This is the formula when there are no tied ranks, where D sub I is equal to difference in paired ranks and N is equal to number of cases. The formula to use when there are tied ranks is this one, where I is equal to paired score. What values can the Spearman correlation coefficient take? The Spearman correlation coefficient can take values from positive 1 to negative 1. A correlation coefficient of positive 1 indicates a perfect association of ranks. A correlation coefficient of 0 indicates no association between ranks, and a correlation coefficient of negative 1 indicates a perfect negative association of ranks. The closer correlation coefficient is to 0, the weaker the association between the ranks. This is an example of calculating Spearman's correlation. To calculate a Spearman rank order correlation on data without any ties, we will use the following data. We then complete the following table, where D is equal to the difference between ranks and D squared is equal to the difference squared. We then calculate the following. The summation of D sub I squared is equal to 25 plus 1 plus 9 plus 1 plus 16 plus 1 plus 1 equals 54. We then substitute this into the main equation with the other information as follows. We have a correlation coefficient of positive 0.67. This indicates a strong positive relationship between the ranks individuals obtained in the math and English exam. That is, the higher you rank in math, the higher you rank in English also, and vice versa. How do you report a Spearman's correlation? How you report a Spearman's correlation coefficient depends on whether or not you have determined the statistical significance of the coefficient. If you have simply run the Spearman correlation without any statistical significance tests, you are able to simply state the value of the coefficient as shown. However, if you have also run statistical significance tests, you need to include some more information as shown, where df is equal to n minus 2, where n is equal to the number of pairwise cases. How do you express the null hypothesis for this test? The general form of a null hypothesis for a Spearman correlation is there is no association between the two variables in the population. Remember, you are making an inference from your sample to the population that the sample is supposed to represent. However, as this is a general understanding of an inferential statistical test, it is often not included. A null hypothesis statement for the example used earlier in this guide would be, there is no monotonic association between math and English marks. How do I interpret a statistically significant Spearman correlation? It is important to realize that statistical significance does not indicate the strength of Spearman's correlation. In fact, the statistical significance testing of the Spearman correlation does not provide you with any information about the strength of the relationship. Thus, achieving a value of a correlation coefficient that is equal to 0.001, for example, does not mean that the relationship is stronger than if you achieve a value that is equal to 0.04. This is because the significance test is investigating whether you can reject or fail to reject the null hypothesis. If you set a value that is equal to 0.05, achieving a statistically significant Spearman rank order correlation means that you can be sure that there is less than a 5% chance that the strength of the relationship you found happened by chance if the null hypothesis were true. And that is all about my report on how to compute Spearman's rank order correlation coefficient for ordinal data.
Good day, ladies and gentlemen. I am going to present the topic how to compute chi-squared test, goodness of fit. So the chi-squared test is an important test amongst the several tests of significance developed by statisticians. It was developed by Carl Pearson in 1900s. It is one of the most commonly used non-parametric tests. In general, chi-square test is used to measure the differences between what is observed and what is expected according to an assumed hypothesis. So chi-square test can be used in chi-square goodness of fit and chi-square test for independence. Chi-square goodness of fit is appropriate for studies with one nominal value, while chi-square test for independence is appropriate for studies with two nominal variables. The chi-square goodness of fit is used with one variable with two or more categories. The test is called the goodness of fit because we want to know if our data fit what we would expect by chance. Although there is no limit on the number of categories for a variable, the test assumes that there is an expected frequency of at least 5 in each category. Suppose we are interested in whether there is a difference in the number of males and females who are reported for cheating. The chi-square goodness of fit is used to test whether the frequency of males who are reported for cheating is different from the frequency of females who are reported. Our hypothesis would state the null hypothesis is the number of males and females reported for cheating will be equal. Alternative hypothesis is the number of males and females reported for cheating will differ. Or in numerical terms, where F is a symbol used to denote frequency. Null hypothesis is the number of males is equal to the number of females. And the alternative hypothesis is the number of males unequal to the number of females. In computing the chi-square goodness of fit test, we make several assumptions. First, one variable with two or more categories or groups. Second, the categories are independent or there is no matching or repeated measures. Third, an expected frequency of at least 5 in each category. And lastly, every member in the analyzed data set belongs to only one of the categories. The process of computing the chi-square goodness of fit is very simple. You begin by counting the frequency of responses in each category, called the observed frequency. Remember from the examples of the nominal data earlier that you can have more than two categories for a variable. We're working with only two categories in this example for simplicity's sake. In our example, assume that a particular school, 8 males and 22 females, were reported for cheating. We would then have observed frequencies for each gender of observed males is equal to 8 and observed females is equal to 22. Next, we determine the expected frequency. Because we expect the number of males and females to be the same, according to our null hypothesis, we expect that half of those reported for cheating will be male and half will be female. Thus, our expected frequency is half of the total number of our sample, or n divided by 2. If we had 3 categories, then we would have an expected frequency of 1/3 for each category, or n divided by 3, and so on. The general formula for expected frequency then is E is equal to n divided by k, where k is equal to the number of categories and n is equal to the total number in a sample. Or for our example with 30 students, n is equal to 30 and 2 categories of gender. So using the formula E is equal to n divided by k, it will be 30 divided by 2 equals 15. The expected frequencies are not always a whole number, nor are the expected frequencies always equal. Suppose we have 30 students who were reported for cheating, and we wanted to know whether frequency of cheating differed by class status, for first year, sophomore, junior, or senior. In computing chi-square, we compared observed frequencies to the expected frequencies because we want to determine whether the difference is greater than 1 would expect by chance alone. We square the difference between each of the observed frequencies minus the expected frequencies because some differences will be positive and some will be negative, and we do not want them to cancel out each other. We then divide the squared differences by the expected frequency in order to weigh them. This is important when the expected frequencies are different. For example, a difference of 2 is minimal if the expected frequency is 20, but 2 is large if the expected frequency is 4. Thus, our formula for the chi-square goodness of fit is the summation of the observed frequency minus the expected frequency squared divided by the expected frequency. Inserting our sample observed and expected frequencies, we will arrive at a value of 6.54. We have to take note that chi-square will always be positive because all of the different scores are squared. If the null hypothesis is true, we expect no difference between the observed and expected frequencies, or that any difference between them will be due to sampling error. The larger the difference between observed and expected, the less likely the difference is due to sampling error. At some point, the difference is large enough for us to conclude that it is due to a real difference in the frequencies in the categories. To determine if the difference is large enough for this conclusion, we compare our computed chi-square to a sampling distribution of chi-square values obtained with the same degrees of freedom as our sample when there is no difference between frequencies. The degrees of freedom for a goodness of fit test are equal to the number of categories minus 1, or degrees of freedom is equal to k minus 1. For our sample, where k is equal to 2, we have degrees of freedom is equal to 2 minus 1 equals 1. The region of rejection defined by chi-square is always in the upper right tail of the sampling distribution because that represents the most extreme differences, or those in the upper 5% or higher, when the null hypothesis is in fact true and there is no difference in the frequencies. The lowest possible value of chi-square is 0 or no differences between the frequencies. As shown in the presentation, figure 12.3 depicts the chi-square sampling distribution, which is positively skewed, and its region of rejection. The alternative hypothesis predicts a difference between the observed and expected frequencies, and our chi-square observed must be greater than the chi-square or in the rejection region of rejection in order for us to reject the null hypothesis of no difference in the frequencies. That would be all. Thank you very much.
Good day, I am Lizelle Bisalao, and for today's we will be discussing the appropriate analysis for independent and dependent group designs with ordinal data. So in this topic, we have the term two-group designs and multiple group designs. But first, let us analyze the two-group designs and its type. So what is independent groups? The independent groups is an experimental design whereby two groups are exposed to different experimental conditions. Usually, half of the participants are assigned to the experimental group where they are exposed to a condition where the independent variable is manipulated. So under these independent groups, we also have the non-parametric test that was used in the category of two-group designs. First, we have the Mann-Whitney test. So according to the slide, it is used to analyze ordinal data from two independent groups when n is less than or equal to 20 per group. For example, you could use the Mann-Whitney test to understand whether attitudes towards pay discrimination, where attitudes are measured on an ordinal scale, differ based on gender. So your dependent variable would be the attitudes towards pay discrimination, and your independent variable would be the gender. Also, we have another one non-parametric test under the category of two group designs in independent groups, which is the rank sums test. So rank sums test is used to analyze data from two independent groups when at least one of the group has more than 20. For example, to form the rank sum test, rank the combined samples given. Then compute the sum of the rank. For example 1, then answer would vary depending on the result of it, and so on and so forth. So the main difference between the Whitney-Mann-U test and the rank sums test is while Mann-U test talks about two independent groups with less than or equal to 20, the rank sums test talks about two independent groups when at least one of the group has more than 20. So other than that, we also do have for dependent groups. But first, what is dependent groups? So independent samples, subjects in group do provide information about subjects in other group. So meaning, the groups contain either same set of subjects or different subjects that the analysts have paired meaningfully. Groups are frequently dependent because they contain the same subjects, and that's the most common example. So under these dependent groups is the category of two group designs. We have one non-parametric test that we use. So it is called the Wilcoxon t-test. So what do we mean by the Wilcoxon t-test? So a Wilcoxon t-test, it is a non-parametric test used to analyze ordinal data collected from two different groups. So for example, the Wilcoxon test can be used to test the null hypothesis that two populations have the same continuous distribution. So a null hypothesis is a statistical test that says there is no significant difference between two populations or variable. So now that we're done tackling the category of two group designs, we will also now be heading to multiple group designs. So for the independent groups, we have non-parametric test to use, which is the Kruskal-Wallis H test. So what do we mean by this? A Kruskal-Wallis H-test is a non-parametric test used to analyze ordinal data from a study with one variable with at least 3 levels. For example, you can use this test under the following circumstances. First, you have 3 or more conditions that you want to compare. Second, each condition you want to compare is performed by a different group of participants in which you have an independent measures designed with 3 or more conditions. On the other hand, for the dependent groups under this category, we also have one non-parametric test to use, which is the Friedman chi-squared. So a Friedman chi-squared is a non-parametric test used to analyze ordinal or ranked data from a study with one variable with 3 or more dependent groups. For example, a Friedman test was conducted on 10 patients to examine the effect that 3 different drugs had on response time. Each patient used each drug once. Results showed that the type of drug used lead to statistically significant difference in response time. So all in all, this non-parametric test that was both used for independent and dependent group. So that's all for today's topic. Again, I am Lizelle B. Salao, the reporter for this topic.
Good afternoon, everyone. I am Richmond Abriel Santos, and I will be discussing why are non-parametric tests less powerful than parametric tests. The key difference between parametric and non-parametric tests is that the parametric test relies on statistical distributions in data, whereas non-parametric do not depend on any distribution. Non-parametric does not make any assumptions and measures the central tendency with the median value. Parametric is a statistical test which assumes parameters and the distributions about the population are known. It uses a mean value to measure the central tendency. These tests are common, and therefore the process of performing research is simple. Disadvantages of non-parametric tests. Number 1. Non-parametric tests can be used only if the measurements are nominal or ordinal. Even in that case, if a parametric test exists, it is more powerful than the non-parametric test. In other words, if all assumptions of a statistical model are satisfied by the data, and if the measurements are of required strength, then the non-parametric tests are wasteful of time and data. Second, non-parametric tests are designed to test a statistical hypothesis only and not for estimating the parameters. Third, non-parametric tests have a less statistical power. If the data are truly normal, a non-parametric test will generally have less power for the same sample size compared to the corresponding parametric test. This means that a non-parametric test may fail to correctly reject the null hypothesis when a parametric test will do so, and we may draw the wrong conclusion from our analysis. This also means that if we are planning a study and trying to determine how many participants to include, a non-parametric test will require a slightly larger sample size to have the same power as the corresponding parametric test. Fourth, non-parametric tests are more difficult to interpret. Interpretation of non-parametric tests can also be more difficult than for parametric tests. Many non-parametric tests use rankings of the values in the data rather than using the actual data. Knowing that difference in mean ranks between two groups does not give us an intuitive understanding of the data. Advantages of parametric tests. Number 1, parametric tests can provide trustworthy results with distributions that are skewed and non-normal. Many people aren't aware of this fact, but parametric analysis can produce reliable results even when your continuous data are non-normally distributed. Second, parametric tests can provide trustworthy results when the groups have different amounts of variability. It's true that non-parametric tests don't require data that are normally distributed. However, Non-parametric tests have the disadvantage of an additional requirement that can be very hard to satisfy. The groups in a non-parametric analysis typically must all have the same variability. Non-parametric analysis might not provide accurate results when variability differs between groups. Third, parametric tests have greater statistical power. In most cases, parametric tests have more power if an effect actually exists. A parametric analysis is more likely to detect it. In conclusion, parametric tests are generally more powerful and can test a wider range of alternative hypotheses. It is worth repeating that if data are approximately normally distributed, then parametric tests are more appropriate. However, there are situations in which assumptions for a parametric test are violated and a non-parametric test is more appropriate. Thank you for listening.
Good afternoon, everyone. I am Carliza Joy Cailio Supe, and I am tasked to discuss some concerns about transforming interval or ratio data to rank data. To start with, our variable may be an ordinal scale because we use ranks as our measurement, such as ranking people on their time to complete a cognitive task, or the data may violate one or more of the assumptions for parametric tests. For example, sample scores may deviate significantly from a normal distribution because of outliers or floor or ceiling effects. The variances of our groups may differ significantly from one another and violate homogeneity of variance, or the intervals of a measure may not be equal. In these later cases, we can transform interval or ratio data to an ordinal scale and analyze the data using non-parametric statistics. Some researchers have objected to using rank order tests if there are several ties in transforming data to ranks, so you should be aware of this issue in analyzing your data. In addition, the transformation loses preciseness in the data and may distort the original data. Still, non-parametric tests gives us useful information about our data and about differences between groups. Let's look at an example. Suppose we gather data on minutes of cell phone use from 10 people and find that although most people reported using their cell phone for 40 to 50 minutes a day, one person reported using the phone for 3 hours and another person reported using the phone for 5 hours. Table 12.12 presents such a distribution. This is a skew distribution, and we can convert the score so that 1. The person with the most minutes of cell phone use, 2. The person with the next most minutes of use, and so on, until 10. The person who used the phone for the fewest number of minutes, in this case 30 minutes. The numbers 1 through 10 now represent the ranks of cell phone use rather than the actual minutes of use. For any two people who use the phone for the same number of minutes, or a tie, we would assign the average of the next two ranks to them. In our example, two people spent 40 minutes on the phone, and the scores greater than 40 minutes were assigned ranks 1 through 6. The two tied scores would be considered to take up the next two ranks, say 7 and 8, and each of these scores would be assigned 7.5 as their rank, which you can see in the table above. If you have several pairs of tied scores, you will then have several pairs of scores assigned the same rank, which might further distort or reduce the sensitivity of your data. This is why some researchers advise against the use of ranked data when you have more than one or two tied ranks. Non-parametric tests for ranks compare the sums of the ranks for those in different groups in a study instead of comparing the means. The null hypothesis predicts no difference in the sum of ranks for different groups because if the groups differ only by chance alone, their sums of ranks should be similar. The alternative hypothesis predicts a difference in the sum of ranks. If we find that one group has a much lower sum of ranks than the other group, we may conclude that the groups represent different populations. As usual, we expect some difference between the groups due to sampling error, but the larger the difference in the sum of ranks, the more likely it is that the group represents different population of ranks. So this ends my topic. Thank you and have a good day.
Good morning. I chose the topic of reducing the chance of a type 1 error. When you reject the null hypothesis, the probability of type 1 error is determined by the criterion level, and you can therefore make your study less vulnerable to a type 1 error by changing your criterion level. Most of the time, the social scientists use the p over 0.05 criterion as they believe that less than 5% probability of making an error is an acceptable risk. The question there, is it really acceptable? Less than 0.5 to 5%. I humbly believe if they are very concerned about the type 1 error, they would use a more stringent criterion such as a p over 0.01. The implications of the findings of a study may lead researchers to use more stringent level. If, for example, you are studying an educational program to prevent plagiarism that is inexpensive and easy to implement, you may feel very comfortable using the 0.05% criterion. If you inadvertently make a type 1 error, incorrectly reject a true null hypothesis, you have not created too much of an expense or bother for those implementing the program and have not harmed the students participating in the program. If, however, your new technique is expensive in terms of dollars or pesos in terms of value or teacher's time and intrusive in terms of students' confidentiality, you may want to reduce the probability of a type 1 error and employ the 0.01 criterion level. The way how I understand it, number one, we need to define state H, defining the sample distribution. What kind of test are we going to use? Is it a 1 or 2 tail test? What kind of criterion level is acceptable? Is it 0.05 or 0.05? After collecting the data and computing the appropriate statistical test and comparing to sampling distribution, the question right now, should we reject H or retain H? Support H with the probability of a type 1 error or not support H because of the probability of a type 2 error. Another common strategy to reduce type 1 error is to use a 2-tailed rather than a 1-tailed test. Recall that the 2-tailed test is a more stringent test because the regions of rejection are split between the 2 tails of the distribution, and therefore the critical value must be more extreme in order for the results to be to be considered statistically significant. Although in theory, a 2-tailed test is used for non-directional hypothesis. In practice, most researchers use a 2-tailed test for both directional and non-directional hypotheses in order to reduce the chance of type 1 error. Thank you, sir. Thank you, classmate. This is my contribution for the topic number 10. Okay? This is Eduardo Miguel Guevara Roldan. Thank you very much.
Good afternoon, everyone, and this is Vincent, and today I will gonna make a summary of non-parametric statistical tools. During a report, we reiterate the distinction between the parametric and non-parametric statistics. So this is just only a brief recap, okay? The key differences between the parametric and non-parametric tests is that the parametric test relies on statistical distributions in data, whereas non-parametric do not depend on any distribution. Number two, non-parametric statistical tests rely on no or few assumptions about the shape or the parameters of the population distribution from which the sample was drawn. If the data are indeed normal, a non-parametric test will generally have less power for the same sample size compared to the corresponding parametric test. Okay, moreover, okay, with regards to the comparison basis and the variables are information about the population, parametric test, the datas are completely known, okay? And for non-parametric test, the data were not known. Basically, it's unavailable. The second one is when it comes to the basis of the test of statistic. Parametric test uses a normal probabilistic distribution, whereas for non-parametric test, the distribution is non-normal or basically arbitrary in nature. And when it comes to measurement level, parametric tests use the scale of measurement in a metric scale, for example, interval or ratio. And for non-parametric tests, we use a nominal or ordinal scale based on order. Okay. And when it comes to the measures of central tendency, parametric tests use the MEN method. And while for non-parametric tests, we use the median method. When it comes to applicability, okay, parametric tests use variables. That's it. However, for non-parametric tests, we use variable at the same time we use the attributes or the characteristic of things. And when it comes to correlation test, parametric tests use the person method, while the non-parametric tests use the Spearman method. Let's continue. And when should we use the non-parametric statistics? Number one rule, non-parametric tests are used when your data is normal. Therefore, the key is to figure out if you have a normally distributed data. Second one, if the sample size is too small, it is possible that you may not be able to validate the distribution of data. Thus, the application of non-parametric tests is the only suitable option. So, what are the benefits of using a non-parametric test? They may be only alternative when the sample sizes are very small, unless the population distribution is known exactly. So you were going to use the parametric method. However, they make fewer assumptions about the data. But non-parametric tests are useful in analyzing the data that are inherently in ranks or in categories. And non-parametric tests often have a simpler computations and interpretations than the parametric test. So these are the benefits while we should use the non-parametric test. And the last one, and how do we decide which non-parametric test to use to analyze the ordinal data? So basically, non-parametric statistics are used when our data are measured on a nominal or ordinal scale of measurement, such as the chi-square statistics and their modifications. For example, the McNemar test are used for nominal data. All other non-parametric statistics are appropriate when the data are measured on ordinal scale of measurement. So these are the brief summary of our report. Thank you so much